Hello, class. Okay, so I'm still sitting on this spinning platform. Got another demonstration. It's kind of fun. Basically just a spinning bicycle wheel. And so, like right now, this platform is free to rotate. So there's very little friction, not much torque. If I spin it, it's not going to be too much torque involved. So at least for short time intervals, there's no external torque. My angular momentum should be conserved. So what I'm going to do is I'm going to spin this wheel. So I'm going to brace myself so nothing happens here. And I'm going to, actually it's only designed to spin one way. Like this handle, if I'm holding onto it, I can only spin it this way. And so spinning it this way, remember the right hand rule, I'm going to curl my fingers in the direction the wheel is spinning, thumb points to the left, so the angular momentum of this wheel is going to point to the left. So right now the angular momentum is pointing to the left, and if there's no torque due to friction, there's no external torque, I'm connected to the wheel, together we're like a system, the angular momentum should remain pointing to the left. So what if I turn the wheel like this? Now the spinning wheel has an angular momentum pointing upwards. But the total angular momentum has to be pointing to the left. So what's going to happen is I'm going to start spinning, and I'm going to create a downwards angular momentum to compensate for this pointing upwards. So we have like a delta V is up, should be 0. So if I introduce a positive, like an upward component of momentum, then I have to turn to create a downward angular momentum. And so, see, downward, I should spin this way. So let's kind of review what should happen. So I can only spin this way. So the angular momentum is like that. So we've got a vector pointing that way. If I tilt the wheel, I'm kind of bracing myself now so I don't do anything. So now there's a torque. Angular momentum does not need to be conserved. But when I let this platform rotate, so anyways, momentum is that way. I'm going to exert a torque on the wheel, and it's going to exert a torque on me. But overall, looking at it from the point of view of conservation of momentum, the total angular momentum has to be that way. And so if I introduce an upward angular momentum, then I'm going to have to spin to create a downward angular momentum. And that's not the whole story, because if it's spinning this way, so yeah, I should maybe have revised what I said, but it's going to be, initially we're at this state. The angular momentum is this way. The angular momentum about a vertical axis is 0. Maybe that's a better way of looking at it, because we're not going to end up with any angular momentum at all. So there has to be a torque. There's no frictional torque due to spinning, but by doing this, I should probably try to rotate this way, but the chair is not going to actually flip over. So there is a torque, but if we just look at this vertical axis of rotation here, initially nothing's rotating around that axis, and our angular momentum about that axis is 0, about this vertical axis. There's an angular momentum in that direction, but that's going to be compensated by torque basically from the floor. So I'm going to twist the wheel this way to create an upward angular momentum, and then I have to spin in a way to produce a downward angular momentum, so I should spin this way when I do the experiment. So let's get this spinning, and then what I'm predicting is I twist it like this, and I'm going to spin like that. Okay, so let's give it a go. Okay, so yeah, spinning the right way to conserve angular momentum about, say, the z-axis of rotation. And if I were to twist it the other way, then I'll spin the other way. So now it's spinning like this. The angular momentum of the wheel is down, and so I'm spinning this way. My angular momentum is up. So we're keeping the angular momentum of about this vertical axis 0 either way. So kind of a fun demonstration with a bicycle wheel. There's actually one more demonstration I want to do with this wheel. I have to set it up though. I think I can do that quickly without having to stop recording. So this one, actually I want to go to the board and talk about this first. Let's make a prediction and then we'll test it with the demonstration. So we'll talk about it first. So I'm going to hold a wheel like this and spin it. So I'm spinning it this way. So angular momentum, to the left. Actually, yeah, the two handles are different. I can hold this one, can't hold this one, and so, oh yeah, I can crank it this way. So anyways, it's spinning that way. I'm using my right hand, but yeah. So angular momentum is to the left. And imagine if we had two strings supporting it, there'd be no net torque due to the strings. Like this string is causing a torque that way. The other string would be causing a torque that would balance it. And then we cut the string. So right now, I want to stop it from spinning because I want to actually make a prediction before we do this. But it was spinning, and then I'm like holding this end for support, but what if I just drop it? This end. So if I drop that, well, when the wheel's not spinning, it just falls. Big deal. But what's going to happen if the wheel is spinning and I drop it? So let's go to the board and talk about this. Yeah, I think we can see it. So let me see how I'm going to actually do this experiment. Yeah, I think I'm going to hold it. Yeah, I can hold it like this and crank it this way. Okay, so it's spinning this way. So let me draw that. So the string is going to be on this side. And then we have our axis here. And from this perspective that you're looking at it, yeah, I'm spinning it this way. So the top of the wheel is moving towards you, the bottom is moving away from you. There's actually some notation that you'll come across later, so might as well do it now. I'm going to put an X here, or sorry, a dot here and an X here. So the dot is coming towards you, the X is moving away. So we can see what direction the wheel is spinning. And so the angular momentum vector is a different color because it's going to kind of. So the angular momentum vector is going to look like this. Okay, now let me write down Newton's second law. In terms of momentum, or angular momentum. So just like F is d, or delta P over delta T, the change in linear momentum over time, the torque is change in angular momentum over time. So if I release it, so it looks like this, we have tension acting upwards and gravity acting downwards. And gravity is going to be basically at the location of the wheel. And so let's calculate the torque about this axis here. So the torque due to tension is 0. And then we have a torque due to gravity, which is going to be into the board. So due to gravity, remember it's going to rotate this way. if I just hold it up, yeah, so it's just like this, and let it go, we can see it's going to fall down this way. It's going to spin that way. And so from the right-hand rule, curl your fingers in that direction, thumb points into the board. That's the direction of torque. And this is the entire reason we even talk about vectors when it comes to torque, since most problems we can handle just by saying clockwise or counterclockwise. So here we have a torque about this axis of rotation that's into the board. And so let's just rewrite Newton's second law. The change in angular momentum should be torque times delta T. So the change in angular momentum should be the same direction as the torque. So what we'd expect to happen is we have this wheel that's spinning, not spinning it right now, but say it's spinning. If I just let it go without spinning, it's going to fall down like this. But if it's spinning, the angular momentum should turn into the board. So it should start spinning like this, like in this direction. So not that way. It should spin. We're going to go closer now that we've made our prediction. So we should expect this end to move away from the camera. So it should move away from you like this. So that's what we should expect based on Newton's law as it applies to torque. I want to keep this cord out of the way while doing this. Okay, so I'm going to spin it. Yeah, one in Grays Lake it's not quite as nice, the wheel. They usually get the better equipment. Let's see if I can actually speed it up this way. Okay, that actually works better. So remember, when I release it, this end here should move towards me away from you. So let's do it. And there it goes. So instead of falling down, the axis does drop a little bit, but then the axis actually starts going in this circular motion. So a very interesting behavior. It's one of those things sometimes I try to think of in terms of just forces, and it's very difficult to wrap your mind around it. Much easier to think in terms of torques acting on it. And if we spun it the other direction, then it would precess in the other direction. But yeah, just a very interesting demonstration, so I wanted to do that. And again, that's the entire reason we talk about torque being a vector. Well, not the entire reason. Getting used to the right-hand rule is important because if you take the next class talking about electricity and magnetism, you will be doing the right-hand rule quite a bit. So it helps to get introduced to it early on. All right, so that's it for the demonstration.